So this video discusses how to find the Thevenin, the Thevenin voltage, and the Thevenin impedance for a AC circuit. Alright, so I put R Thevenin there, but technically it should be a Z Thevenin. Alright, and so one thing I want to point out to you is be sure to redraw the circuit anytime that you need to, so that you have just rearrange the elements a little bit. So to find Thevenin, we have to open the circuit at the terminals. Okay, so remember Thevenin says that you're going to break the circuit at 2 points. Alright, so here we've got the points are A, B, but it could be any, break any two, break the circuit at any 2 points, and then you can find the Thevenin and the Thevenin. So the Thevenin, we're going to open the circuit at these 2 points. So we're basically just going to take out this capacitor. And we're just going to wipe that capacitor out there. And then we can find the voltage at that point. So effectively what we're going to be doing then would be putting a voltmeter in place. And so if we were able to just stick the voltmeter in there, and we can actually measure that. So when you do the lab, that's one of the things that they'll actually have you do, is simply open the circuit and measure that voltage. So effectively we'll put a voltmeter here and measure this voltage, and this is going to be Thevenin. To find Thevenin, the impedance, we need to short all the voltage sources and open any and all current sources, and then find the impedance at AB. So if we had an impedance meter that could actually measure the impedance, including the capacitance and the inductance, then we could actually stick a impedance meter there. Alright, so let's start by finding a Thevenin, and as I said, we're going to redraw this. Okay, so we're going to have our AC circuit, and what we want to do is you need to label these nodes, right? So we're going to come up here and just mark this as node A. Okay, so this is node A, and so at node A here we have R1, which is 2 ohms, and that is in parallel then with X of C1, which is minus J 8 ohms. Remember, it's a capacitor. Alright, so, and changing colors helps also if you have it available. So I'll call this point B, and so this is point B over here, and point B then we're going through an inductor, and then we're going to go to ground. Okay, so this is our ground down here. And so then on the other side of the capacitor now we have C. Okay, and so this is point C, but now point C here is connected to point B through a 10 ohm resistor. Alright, and then we had, of course, X of L was over here, which was J 4 ohms. Okay, and so I redrew this, but I want to actually redraw it one more time here and make it even just a little bit neater. So we're going to have our 2 ohm And again, you could go back through and label those, right? So this is node A up here. And, sorry, this is a capacitor, minus J8. And then there's a 10 ohm. Okay. And then these now are connected together. So this was point B. And you could color code it too, but I'm not going to take the time to do that here. But this is node B, and then that goes to ground. Alright, so now that we look at this, then we can see that these two are definitely in series. So I have a series combination here of 10 minus J8. Okay, so that's this series combination. And then that, of course, now is going to be in parallel with this 2 ohm. Okay, so I'll call that's kind of a green color here. I'll call this Z parallel, two parallel lines. Okay, so Z parallel is going to be a 1 over 2, 1 over 2 ohms plus 1 over parentheses. Do not forget your parentheses here, 10 minus J8. Alright, and that'll give us this parallel combination. So if we want to calculate that, an easy way to do that is in the Octave software. So we'll have Z parallel. Well, I can't use that. I'll just call it Z11 because they look kind of parallel. And so that is going to be 1 over parentheses 1 over 2 plus 1 over parentheses 10 minus J8. Okay, and so that is the parallel combination. Now you need to multiply J times 8. Alright, so that gives me then this particular value right here, which is my Z parallel. And so I'll just kind of paste that in here. Okay, so there's my Z parallel combination. Okay, remember the I and the J they both just represent that 90-degree phase shift inside the AC circuits. Alright, so now this Z parallel then is in series. Okay, so the Z parallel, and it doesn't hurt to redraw these if you need to. And so we're going to have now our voltage source is in series. We have this Z parallel branch. That's supposed to be a Z there. Z parallel. And then the inductor, which is plus J4 ohms. Alright. And so we add that together so we can get the total impedance as seen by our source. Okay, so we get the total impedance as seen by the source. Z total as seen by the source, so just spell that out. And that is simply Z parallel plus the J times 4. Alright, and so that gives us this value here now. 1.762 ohms. Plus 3.8462. Okay, and so that is the total impedance as seen by the supply voltage. Okay, so that's what's seen by the supply voltage. So now we got to go back through, and we're looking for the voltage from point C. Okay, so we're looking for the voltage from point C up here to ground. Okay, so that's the voltage we're looking for. So we have to then go back through and calculate your current through the 10 ohm and find like the voltage at VB and then the current through the 10 ohm and add those together to get that. Or we could find the current through the capacitor and subtract the voltage to find VA there. So however you want to do it. But what we have to do now is we've got to find the voltage. Basically, Thevenin is the voltage right here at point C. So we have to go back through and find that. So we have the total impedance, so we can find the total current. So we can find the total current by the supply source, okay? So that total current is the total voltage, which was 50 volts, angle 0, divided by the 1.7692 ohms plus J 3.8462. So remember, J and I are one and the same here. The calculators like to put I in there, but we like to use J so we don't confuse the I's with current. Okay, and so we can calculate that total current. And so I supply current here is the 50 volts divided by the Z total. Okay, and this is the rectangular form of that. And I'm just going to keep that value here right now because we're not asking for that, so we don't really care whether it's in rectangular or polar, just whatever form that's in. But I'm going to make a copy of that so I don't lose that. Okay. And now that we have that current, we can find the voltage VB, okay, because that's the current through the inductor. Okay, so that is the current through the inductor, so we can find the voltage VB. So we get that the voltage VB to ground, okay, so VB to ground there is this supply current, IS, times our inductor, which is J4. Alright, so remember this is an inductor, so we're going to have the current is going to be lagging behind the voltage. So the voltage is going to be 90 degrees ahead of that, and that's what that J is telling us. Alright, so we're going to say that the voltage VB now is equal to IS times J times 4. And so we get this 42.9 volts. At an angle plus 19.7 volts J, okay, and we could calculate the polar form of that, but again, I'm not too concerned about the polar form right now, whether I'm in rectangular or polar form, because I'm just trying to find the values. And so when we find the value, when we put it into Blackboard, we're going to want to put it in polar form. But my calculator that I'm using, this Octave software, likes rectangular form, so I'm just going to leave it in there. I've got VB here, is this value, but we still need to find the voltage, or from B to C. So we need to find the voltage through this 10 ohm. Okay, so I need to find the current through the 10 ohm. So what I'm going to do is I'm going to calculate the voltage from VA to VC. Okay, so the voltage from VA to VC is my supply voltage. This is just Kirchhoff's voltage law here, so I'm just applying Kirchhoff's voltage law. It's the supply voltage minus VB. Okay, and so remember, if we look at the original circuit, my supply voltage up here was simply 50 volts. So I'm going to take the 50 volts minus the VB, and again, I can just do that very easily in the Octave software here. So I'm going to say that the VAC voltage, the VAC is the 50 volts with no angle minus the VB value. And so there you can see that's my value of it, and again in rectangular form. Okay, and so that's my VAC value. Put that right there. So this is my VAC value. And now I know the voltage from VA up here, from VA to VB, right? I'm sorry, I said AC, but that was actually AB. That was the voltage VAB. I stated that wrong. Okay, because that was the voltage from here to the B value, not the C. Okay, so we still got to find the VAC, so that was the B value there. All right, but now we know the voltage across this impedance here, this 10 ohm resistor plus the capacitor impedance. All right, so we know that now. And so we can use Ohm's law. So all I'm really doing here is using Ohm's law and Kirchhoff's voltage law. So right here was Kirchhoff's voltage law, but this was simply Ohm's law, and this voltage was Ohm's law. Okay, so we found the total current by finding the total impedance and then using Ohm's law, voltage divided by the impedance. And that gave us the total current. Then we used Ohm's law here. We knew the total current had to flow through this, right? The total current had to flow through the inductor. And so we used Ohm's law again to find the voltage there. And then we used Kirchhoff's voltage law to find this voltage, because we took the supply voltage minus VB, and that left us with the voltage VAB. So now I'm going to use Ohm's law one more time. So all we're doing is applying Ohm's law and Kirchhoff's voltage law, and if you need to, maybe Kirchhoff's current law, and we can just figure out what's happening in this circuit. So to find the current in here, that's Ohm's law one more time. Okay, so we're going to find the current through just this impedance here. Okay, is the voltage, which is VAB, the voltage VAB. So the current through my 10 ohm, which is also the current through the capacitor, but I'm just going to mark it as current 10 ohm because that's what I need to do. I need to find this voltage. I already have this voltage. If we add these two voltages together, we'll have Thevenin. All right, so the 10 ohm is going to be VAB divided by the 10 minus J8. And that'll be the current through the 10 ohm. And so I'll flip back to my calculator. So I'm going to have I10 ohm is equal to VA. I remember I mislabeled that, so I'm going to correct that. VAB was that voltage, and that, so what I called VAC before is actually VAB. So now I'm going to say my I10 ohm is equal to VAB divided by parentheses. Do not forget your parentheses. 10 minus J times 8, the capacitor piece. Okay, so that is the total current. That is the total current through that resistor. And then I can then calculate, using Ohm's law one more time, I can calculate the voltage across the 10 ohm, which is the current times 10, right? Times 10 ohms, 10 ohms resistance. So the current through the 10 ohm resistor times the 10 ohms gives me the voltage across the 10 ohm resistor. Okay, but the voltage that we're looking for here is this voltage. And so this voltage here is the voltage across here plus the voltage across there. So the voltage V Thevenin, that wasn't very straight. The voltage V Thevenin is actually the voltage across the 10 ohm resistor plus the voltage across the inductor, okay, which I've called VB. Alright, and so all we have to do now is add those two voltages together and we'll have V Thevenin. So we have the VB voltage, and I'm going to add the V10, the 10 ohm voltage, and that is my V Thevenin voltage. Okay, and so this is the rectangular form, but again, when we want to put this inside a blackboard, when you put voltages inside a blackboard, they should be in polar form. So I'm going to make this in polar form. Okay, so remember, polar form, you have to basically take Pythagorean's theorem, all right, and the absolute value function will do that for us. Okay, so I'm just going to use the absolute value function built in here. And then there's the angle function, which will give us the angle, but it gives us the angle in radians. So I'm going to multiply that times 100 and divide by pi radians, and that will get us the angle. So here we have V Thevenin is 57 at an angle of 11 degrees. Okay, so V Thevenin is 57 volts. Is 57 volts here at an angle of 11.102 degrees. So if we were going to put this in a blackboard, this 5 would make the 9 round up, so we would have 58.0 volts at an angle of 11.1 degrees, and that would be our answer. 11.1 degrees, and so that would be our answer then that we would type into Blackboard for V Thevenin. Okay, so this is V Thevenin. So again, how did I get that? I mean, it seemed like it was quite a bit of calculations. However, the only things I had to do was Ohm's law. This was Ohm's law. Then I used Ohm's law again. Then I used Kirchhoff's voltage law. Okay, so Ohm's law and Kirchhoff's law, as we've talked about before, these are the only things we really needed to do this. And then here's another Ohm's law. And this is Kirchhoff's voltage law again. Okay, so I applied impedance reduction to to simplify the impedances down to a total impedance as seen by the supply voltage, and then I used Ohm's law, and then I used Ohm's law again, then I used Kirchhoff's voltage law, I used Ohm's law, and I used Kirchhoff's voltage law, and that was able to get me to that voltage. So now let's take a look at getting the impedance. Alright, so we go back to the original problem, and what we're going to do here is we're just going to come in here and we are going to remove, we're looking for Z Thevenin now. So what we're going to do is we're going to short all the voltage sources. So I'm going to take out all the voltage sources and replace them with a short. If it's a current, I'm going to replace it with an open circuit. Alright, so again, we're looking for the impedance at these two terminals. Okay, so we're looking for the current at these two terminals, and we do that by shorting out all voltage supplies, opening all current supplies, and then just calculating the current. So as we did before, we need to redraw this. So I called this A. So this was A before, but now this is all shorted. So now this is all node A. Okay, so this is all node A. So if you look at this, what do we got attached to node A? Well, we have R1. So here's node A, and we have R1 coming down from it. And then we have our capacitor minus J8. Let's see, R1 was 2 ohms. This is a J here. Minus J8. But look at this. We also have this inductor. So we also have an inductor here of J4. Okay. And so this was all node A up here. So now, I'm going to change color here. We'll look at this one here. Here's a node. We'll call this, I think I called this node B before, so I'll call it node B again. So here is node B. Now node B, the inductor is attached to node B, and R1 is attached to node B. Okay, so R1 is attached to node B. Oops. So this is node B, but and this 10 ohm, there's this 10 ohm here. Okay, so there's a 10 ohm, and it's attached to node B. And again, you may have to redraw this a couple of times till it looks right. I'm not quite sure whether we're doing real well yet. Okay, so I'm just kind of doing this on the fly. So I'm going to create a different color, and we're going to call this node C. Okay, so this is node C, and the capacitor and the R2, 10 ohm, meet at C. Okay, but remember, this is point AB. So what I'm trying to measure, what I'm trying to get here is this point right here. Okay, and so I need to maybe redraw this again. So I'm going to have, I want like an open here. So this was my point C, and I had the 10 ohm. Resistor, so that was R2, and then I had my capacitor, that was X of C1. Alright, and now R2 went to point B. Okay, so R2 went to point B, which I had in blue. Okay, so this was point B, But now point B, see R2 comes this way, and I can either go up through R1 or down through XL. So that means those two are in parallel. And again, you just need to redraw this till it looks like something you can work with, okay? So the first time you redraw it, it doesn't look quite right. You just have to redraw it till you get something a little bit better. All right, and then we had red, okay? And so this guy here and this guy here is point A, okay? And that is this lowercase b right here, right? So this was lowercase b, this was lowercase a, and this is what we're looking for. So now I've got something that I can work with here. So looking here, right, we can clearly see that the blue section here, that this blue section, these two guys are in parallel, and then they're in series with R2, which is then in parallel with the x of c. And so again, you just have to redraw till you get something you can work with. So we have here this this box here, so I'm going to call Z box. Okay, Z box is this parallel combination of 1 over R1, which is 2 ohms, plus 1 over J4, the x of L. All right, and so that gives us our Z box value, and we can pop over to our octave here and calculate that. So I'll call that Z box is equal to 1 over parentheses 1 over 2 plus 1 over parentheses J times 4. Don't forget those parentheses or you will have the wrong answer. So that is a 1.6 plus J.8. Okay. So we have a 1.6 ohms plus J 0.8. And again, if you want 3 significant digits there, you would have to add those zeros in there. All right, but that's the Z box. Now Z box then is in series with my R2. So we'll call this like Z box R2, okay, and just combine it together. That's in series, so we're just going to add the 10 ohms to that. So that's going to give us 11.6 ohms, and there's my 3 digits now, 11.6 ohms plus J 0.800 ohms. And then this whole section now is in parallel with the capacitor. All right, so ZAB, Z lowercase a to b, is that impedance that we were looking for. So that is our Thevenin impedance. Okay, so there's our Thevenin impedance. And so that's just 2 parallel combinations. So we have this 1 over this Z box R2 thing going on, plus 1 over our capacitor, so that's going to be a minus J, and then our x of c value. And let's see, our x of c value was 8. Okay. All right, so now let's, I'm going to flip back to octave then to calculate that. Okay, so the first thing I got to do is build inside of my octave the Z box R2, right, which was equal to Z box plus that extra 10 ohm resistance, right? So 11.6 plus J 0.8. And then we need to put that in parallel. So Z Thevenin, which is also ZAB, is going to be 1 over parentheses this 1 over Z box R2, and I can just type in that variable when I'm in this Octave software, plus a 1 over minus J times 8, that's that X of C piece, and there is my value. So Z Thevenin, so now I have a Z Thevenin circuit here. My Z Thevenin is this 3.9828 minus 5.5279. Okay, and so notice it's a negative sign, so that tells me it's a capacitor. So we could draw our V Thevenin. Okay, so here's my V Thevenin. And we could just kind of draw this generic box here, call this Z Thevenin, and it would be that value, and that's my node A that we started with, my lowercase a, and this is my node lowercase b. All right, and so but in this box, I know there's a capacitor and a resistor in this box, because when you look at these Thevenin values, you know that this is resistance, the real value is resistance, and then this is a negative sign, so that's obviously a capacitor. And so we could come back over here and draw this now. So we can draw the V Thevenin circuit. All right, and so V Thevenin was this 58.0 volts at an angle of 11.1 degrees. And then we have resistance. So we have a resistance of 3.98 ohms down to 3 significant digits. And then we know that we have a capacitor, right, which is minus J 5.5279. So that 7 is going to round up and make that a 5.53 ohm impedance in our capacitor. So this is point A, and this here then is point B. All right, so that is our Thevenin equivalent circuit. All right, so once we do that, we can then say, well, what is going to give us the maximum amount of power? How do we get the maximum amount of power to the load between nodes A and B? And the answer for that is we use the for maximum power transfer, okay? Max power transfer, all right? Maximum power transfer occurs when the load impedance, so if we just called this Z load here, when the load impedance is equal to the complex conjugate, so this star means complex conjugate of Z Thevenin. And what that means is if this is negative, you make it positive, and if it's positive, you make it negative. So Z load should be a resistor, Z load for maximum power transfer. So that what we're saying is we're gonna get the maximum amount of power from our supply over to the load through this Thevenin impedance. We're going to get maximum power if the load resistance was 3.98 ohms and there was an inductor with a impedance of positive J 5.53 ohms. All right, and that is the maximum power theorem. So this means complex conjugate. What that means is that if you got a capacitor in your Thevenin, then you put an inductor in the load. All right, and what happens is you make them the exact same value, so the capacitor and the inductor cancel out. So if you have an inductor if you actually had an inductor in the Thevenin impedance, then you would put a capacitor in the load to get maximum power transfer. All right, and so what happens is you set this value. This is a plus J5.53. This is a minus J.553. The J's disappear, and all you're left with are the resistances within the circuit. All right, so and that's kind of another way of saying resonance. When the impedance of the inductor equals the impedance of a capacitor, okay? I mean, I was drawing an inductor there to just say if you had an inductor there, but there was actually a capacitor here, right? Go back in the video and look at that. And so you put in if you have a capacitor, you put in the load an inductor that matches that impedance, okay? If in your Thevenin you have an inductor, then you would in your load put a capacitor that has a magnitude matching that reactance in there, and that will give you maximum power transfer. So that is Thevenin's circuit and maximum power transfer in an AC circuit.